the supervisor was Matteo Paris, and the University of Turku, Sabrina Maniscalco and Matteo Rossi were also supervising this work. So I think we can start. Today he will tell us about search and noisy graphs with continuous time bounding breaks.
Yes.
And just a few words, after this seminar at 12 we will start another seminar, so today quantum networks, and Albert Cabot will be in the seminar.
Okay. So I have written here Università degli Studi di Milano, but actually I'm a freelancer researcher for some weeks yet. So, and today I will talk about searching on noisy graphs via continuous time quantum works, and now I will explain the meaning of all this. And as Roberta said, I started this work with Matteo Paris in Milano, and it was my master's thesis basically. And then I got translated into Finnish Sauna, and I worked with Sabrina and Matteo at Turku. And where you can see that the Turku quantum technology group is invaded by Italians as well. So what I will talk about in this talk, first of all, to introduce continuous time quantum works, I must tell something about graph theory, but I assume that you already know something about this, so I just briefly review it. Then I will talk about the problem of quantum spatial search, but it's in a certain way the main subject of my talk, and it's a quantum computation algorithm based that may be based on continuous time quantum works. Then I will discuss how we can introduce noise in continuous time quantum works, and what's the meaning and why we want to introduce noise in a continuous time quantum work. I will give the results about the noise, because this is more or less my work. And finally, I will propose some outlook and ask for some suggestions. So basically, in the talk, we will have two different parts. A first part of it will be quite long anyway, in which I will introduce all these problems. And then a second part where I will discuss the original work in a certain sense about noise. So just to talk with the first part, very briefly, graph theory. We know that a graph is a connection of nodes connected by links, and with a graph we can describe any kind of network we can see in our world. As you may know, the most important tool to describe a graph is the adjacency matrix, and essentially in the adjacency matrix we have a 1 if there is a link connecting node 1 to node 3, here in this position 1, 3. The adjacency matrix is symmetric, and using this we can describe any type of graph. Another important matrix is the degree matrix. In the degree matrix we see at position 3, 3, for instance, 4, if there are 4 nodes outgoing from the node number 3. So it tells us essentially how many links are outgoing from a certain node. And finally, I'm going very fast because I assume that you already know, the Laplacian matrix is the last matrix I'm defining, and it's defined basically as the difference between the degree matrix and the adjacency matrix. And this Laplacian matrix is the most important matrix for my talk, and now I will explain you why. Because, first of all, I want to talk a bit about continuous time classical random walk. So it's quite a well-known problem. We have a certain walker that at time 0 we assume it starts localized in a certain node. And this walker can jump to another node of our graph according to a certain hopping rate. What we want to find is essentially we let the time go by, and we want to find the probability distribution over the nodes of our walker at a certain time t. We describe it using this vector where we write P1, Pn, where n is the number of nodes of our graph. And this is a very well-known problem in classical physics. Okay, so it's quite easy to see that if we want to find that vector at time t, the probability of being in the node j at time t plus dt, where dt is infinitesimal, It's given essentially by two contributions. One is the probability of getting to the node J, jumping from all the other nodes, and it's proportional to the adjacency matrix. The second contribution is the probability of starting from the node J and jumping to any other node to which the node J is connected. So we see that there is the degree matrix. So we recognize here the structure of the Laplacian matrix, the differential equation describing the continuous time classical random walk is this one, where we have defined the hopping rate I was talking about before here. And finally, the solution is quite easy, and it's this one. It's a negative exponential, where the Laplacian matrix is the generator of the time translations. So it's quite a nice result. It is completely classical, and we can obtain our solution of a classical continuous time random walks quite easily. So why am I talking about this classical model? Well, the fact is that when you read in the literature quantum walks, you have to remember that there are two kinds of quantum walks, the discrete time and the continuous time. And they are totally different one from the other. So today, I'm talking about the continuous time quantum walk, and it has nothing to do with the discrete time version. Okay. So the nice thing about continuous time quantum walk is that the definition of the continuous time quantum walk is essentially a straightforward generalization of the definition of continuous time classical random walk. Indeed, if we go to the definition, we see that in the classical case here, for the state space, as I mentioned before, we have the vector of probabilities P1, P1, Pn on the nodes. In the quantum version, obviously, we want an Hilbert space. And it's the same. It's the Hilbert space of the span of this basis. This basis is the basis of the single particle states localized in the nodes of the graph. The difference, of course, is that now we have any kind of state given by this superposition, and here we have amplitudes. Talking about the evolution, in the classical case, as I proved before, the classical case, the evolution is given by a negative exponential with Laplacian as generator. Quantum case, well, the same, but we want a unitary evolution because we are quantum now. And so the Laplacian is still the generator, but we put an I. Finally, the probability conservation in the classical case, it is expressed as the fact that the sum of all the elements of any row or column of the Laplacian matrix is 0. Here we just have to require that our Hamiltonian is Hermitian and the Laplacian indeed is, because it's real and symmetric. So we are fine. This is a general definition given by Fari and Gutmann in '98. It was for studying a certain problem of running through an exponential, running through a balanced trees, so a sort of a computational problem, so quite abstract. But if we wonder about this definition, where is the quantumness in our definition? I mean, what is the difference between this and the classical case? Well, if you think about it, there are actually only two big differences that are, first of all, the fact that before we had a vector of probabilities of being in each node. Well, now we have again a vector, but it is a vector of amplitudes. So if we want to get the vector of probabilities again, we must apply the squared modulus on all the elements. Second definition, obviously now we have an I in the evolution. So our walker behaves in a certain way like a wave. We have interference between the different paths of our quantum walk. And well, these are actually for real only two differences between classical and quantum. And the nice thing is that if you think a bit about it, these are for real, in general, the differences between classical and quantum when we have to separate these two scenarios. And just to see the effects of this difference, this is the simplest case of a continuous time quantum walk on a line, one-dimensional lattice, that's graph. And in the classical case, as you recall, the probability distribution is a normal distribution. This one, the classical Brownian motion, essentially. where we have a big peak in the position where we started the walk. In the quantum case, we see this weird shape with two peaks going toward the edges of our lattice. And the nice thing about all this is that classically the variance is proportional to the time, while the quantum case, the variance is proportional to the time squared. So it's usually said that the quantum walk is faster in a certain sense, but the continuous time random classical walk. Okay, so as I said, continuous time quantum walk is just a theoretical model. It has actually a lot of applications, for instance, also in the transport into material at the nanoscale, also biological transport. But today I'm going to talk only about one of these applications, that is quantum spatial search. But it's a quantum algorithm related to complex quantum networks. This algorithm is related to the famous Grover's algorithm, that is one of the two very big and famous algorithms of quantum computation. The other one is the one offshore for the factorization and cryptography. And essentially, Grover studied in '96 the problem of finding a certain element with a certain property in an unordered database. That is essentially finding a number in a phone directory. Very simple. In the classical case, obviously, we have to live through all the phone directory, and we find this number in a time that is of the order of n, where n is the number of elements. Grover proved that if we use his quantum algorithm, we can do it in a time that is only the square root of n. So this is the algorithm. The quantum spatial search is the same problem, but instead of having an unordered database where all the elements are abstract elements in a computational way, our database is a spatial database where all the elements have a given position in space, and they are connected or not by some links. That is to say, our database is a graph, and we have our target node that we want to find. So it's a generalization of the problem of Grover. The fact is that obviously we cannot apply the same algorithm now because of reasons of locality, essentially. We violate relativity if we try to use this algorithm here. So what we need is a quantum robot. Here it is. Our quantum robot has to run over our lattice, and it has inside an oracle function, and this function tells us whether or not the node we are examining is our target node. Okay, so this is the problem. Childs and Goldstone proposed in 2004 an algorithm based on continuous time quantum walks that can solve this problem. And this is why I'm talking about all this. Well, the algorithm is quite simple, and here we start in the true part of what we want to discuss today. This algorithm needs an Hamiltonian that is this time the Laplacian of our graph, that is the database, times a certain coupling constant, gamma, and we add the potential well on the target node. So then if we start in this initial state, that is the maximal superposition, we basically just run our continuous time quantum walk using this Hamiltonian, as I described before, and we measure in the computational, in the nodes basis, we measure at a certain time t, our state, and we want to find our target node after the measurement with the maximal probability possible. So it's all played on finding the right gamma, to tune this gamma in the right way to get the maximal probability for a certain time t.
What do you mean by finding the node? I'm confused.
It's finding the?
Finding the node. What is finding? In the classical goes
in the quantum case, we literally measure. We want to measure this node, finding in the sense that we want our state to be the state of a localized particle in the node after the measurement.
So classically, to have the defined probability is 1 in the node.
Exactly, but also quantistically, we want this. Yes. Yes, classically, we want to find the name of this node. I mean, if we have numbered all the nodes from 1 to n, we want to find what is the node with this given property, the number j. Quantistically, we want that after the measurement, our state is completely, or the most we can do about it in this node. Indeed, for instance, there are some topologies where this works, and for instance, the complete graph, the graph in which all the nodes are connected to all the others.
You compute the probability of being on that node.
Exactly. Here it is. This one is the probability of measuring the target node as a function of time. As you see, at a certain moment that is of the order of the square root of n, if we measure, we find the target node. So obviously we want this peak to be the highest possible. In this case, literally you are in the target node, but there might be cases in which you are not exactly on it, but we want this probability after the measurement to be the maximum possible.
You started with a kind of couple state at the beginning.
Yeah, the maximal superposition.
What happens if you start with another one?
It's a good question. The fact is that they decided to start in this when they defined the algorithm, because in a certain way it is the most general. I mean, assuming no information before our search, we say it's...
In a classical one, you will start from another node. There will be a concentration and you want to split in the network.
It's true, and...
In this case, it's the other way around. You already split, and
yeah.
you can detect the node.
It's true, and I can agree. You can decide to start in another node. Somebody did it, but in the normal framework, this is it. Actually, well, it can be useful to start in that node to think about more implementation. For instance, let's reverse the dynamics. Since we are unitary, this would be the problem of I start in one node, I want to get to the maximum proposition. So it can be useful, but I totally agree that it's a good point.
I have a question.
Yes.
I don't understand. So the quantum system Hamiltonian is connected with the energy.
T? Yes.
Here, somehow express the Hamiltonian in terms of this Laplacian and then this projector. And so it's not here that this is energy? So what do you call this operator Hamiltonian?
Speaking about the quantum information framework, I would say that I call it Hamiltonian because I can, in the sense that this is an Hermitian matrix. So I mean, my reasoning is that I want to do something for which this is useful. I define it theoretically, not thinking about what energy can be. And this is a true Hamiltonian, and the fact is that I will think later what is this related to energy. I mean, of course it will be an energy, but it will, if you're asking me which kind of, I mean, the energy of what this is, well, I would say I still don't know. When you realize it in a laboratory, then you will understand what is the energy of this. But in the quantum computation and information framework, usually, I mean, it's true that it's a bit abstract, but we invent Hamiltonians and we say we are happy with them, and then we will see.
If you go back, the evolution operator
Yes.
was L. Yes.
Here.
The evolution operator is L or H.
Well, it's the same. Nu0 times L is H. It's the Hamiltonian of the... Well, maybe I didn't explain it.
Not in your example, not in your...
Yeah, exactly. We are a bit changing this.
Okay. You're using it.
Instead of just using L, we are adding this potential well with a certain coupling.
Okay.
This is the algorithm. But then we run the same continuous time quantum walk. So the fact is that there are a lot of topologies where this work. Just to say one thing, maybe you're not from the quantum information field, but the fact I can understand that this looks a bit weird and abstract, but this is how quantum information theories work. We build Hamiltonians as we see, as we like, And we say that this Hamiltonian, okay, it's not exactly the continuous time quantum walk Hamiltonian, but it changes nothing. I mean, we do the evolution in the same way. We just find the suitable Hamiltonian, but the important thing is that we respect the structure of the graph. This is the important thing for a quantum walk. And then we let it run, but I mean, it's, in a certain way, it's a toy that can be useful, but it's a toy that we use. So, speaking about topologies, there are more topologies where the algorithm works. And for instance, the hypercube or the d-dimensional lattice, but only for d greater or equal to 4. So it's not something that you can see, let's say. It's not. It's Euclidean, but it's on higher dimension, but in the real world. So first, original part of this talk. For now, it's all in this paper. But in our work, we managed to prove that there is another graph topology for which the algorithm works, which is the star graph. The graph in which we have one central node connected to all the others, and there are no more links. And we prove that if we run the algorithm on it, independently of the target node, we find the solution in the time of the square root of n, and we find it with a probability that is close to 1. So it's optimal. Not only it is optimal in the computational limit of n, so number of nodes way greater than 1, but also for few nodes. For instance, when n is equal to 4, if I remember correctly, we already have a probability of 95% to get our target node. So it is very good. And
order is part of n?
yes, n is the number of nodes.
That's the time to reach the...
This one is the time,
That's the time.
and this is the probability.
And
Yes.
this is 1 over...
No, probability, it doesn't have exactly
Yeah, the
1,
other.
but
Yeah.
it's...
Yeah, you're right. Yeah, you're right. This is 1 over, it has a minus, yeah.
But they do the observation in here, because what you have is the wave function there, all over the network, and then you want to observe the particle in the node, so you have to collapse the wave function. How, which is this?
Yeah.
Observation here.
This is, no, of course, no. Yeah, it's another very good question. It's a problem. I mean, it's a problem, I would say, of the experimentalist, but I will then try to convince you that it's feasible.
Okay.
Yeah, of course, you have to find experimentally a way to measure our graph.
The operator that you apply to the...
Exactly, but they can do it.
Okay.
So, and yes, we are basically using the projector of our node basis operators. Yes, we have to understand where it is. But I mean, it can be done, of course, thinking about energy. You are searching where is the energy in our graph, in our physical graph. So right now, I want to convince you that this finding is very interesting and very important. So I open a digression about it. And let's talk a bit about the implementation of continuous time quantum walks, so you see that these weird things can be done. The first one was in 2008, and it was based on optical waveguides. And it's actually a very clever idea. First of all, this is a continuous time quantum walk on the one-dimensional lattice, so our line, essentially. What do? We take a layer of waveguides. These ones are the waveguides. Each waveguide is a node. So here is our lattice with all the nodes. And we let the light go through this layer of optical waveguides, and we couple each waveguide in a way in which we are jumping, like doing the open rate, like in a continuous time quantum walk. And the fact is that if we let the light go through this layer of waveguides, well, the clever idea is that basically we are describing in two spatial directions, so this one and this one, the one spatial direction of the lattice, the one-dimensional lattice, and the one time direction of the evolution of the walk. So what I mean is that here is our direction of the lattice, where we find it like our line. In this continuous direction, we are actually observing our continuous time quantum walk go by our layer. So we are literally observing the evolution during time of a continuous time quantum walk. for instance, another paper, again, Waveguides in 2010. Here you can see what I mean. This is a one-dimensional continuous time quantum walk, but you're seeing the complete life of a continuous time quantum walk. This is the line. In the continuous direction, that is spatial, but you can see like if we are observing the time. So finally, again, Waveguides, a few months ago, this paper. The only difference, the technique is always the same, very clever. The only difference here is that they managed to implement it on a two-dimensional lattice. Doing what? Well, instead of having a layer of waveguides, we have a solid cube of waveguides. And in this case, we have here our two-dimensional lattice. So in this direction is a two-dimensional lattice, and then we have the continuous direction going through our solid cube of waveguides. That is the time again. And if we search for them, these are, well, there are more papers about the same techniques, but this is the only way they are implementing continuous time quantum walks by now. Well, now one can wonder about, is there an implementation of quantum spatial search, the algorithm I was talking about? Well, if we think about it, we don't find them. There are none. And well, it's quite easy to understand why there are no so far. Just think about the topologies we were discussing. For instance, the complete graph. It has a lot of links that intertwine. The topology is really complex. And if we go back to waveguides, of course, we are coupling only the first neighbors, but we cannot couple this waveguide with this waveguide. It's not feasible. So, talking about all this, to go back to my cute star graph, and you can see that the star graph, it has a quite simple topology. Okay, there are still some problems because these two are not coupled. But, I mean, for instance, we can at least map it on a Euclidean plane. So this is quite good. It's a step forward, and another hope is given by this other paper a few months ago. This is an American group working on superconducting qubits. And circuit quantum electrodynamics, that is, I don't know if you know it, but it's the technology of the wave, the first maybe quantum computer, and so on. So these superconducting qubits connected one with the others. This is a picture, so this is real world. And they managed to build an hyperbolic lattice, that is a lattice in which our nodes are not distributed according to a Euclidean geometry like before on the lattice, but the geometry is hyperbolic. So here, where you see this coupling with three things around, here it is a superconducting qubit that is a node of our graph, and they are connected. And we managed to build this lattice. And the Hamiltonian of this lattice is exactly the Hamiltonian of the pure continuous time quantum walk. For our purposes, we should add a potential well on the right node. And, well, our hope is that the star graph is obviously not an hyperbolic geometry, but it looks like. So our hope is that using the same experimental technique, they can manage to implement the same thing with our star graph. And just to answer your question about the measuring, well, they manage to measure the energy of this lattice. And that means they manage to localize where our worker is. Okay, so this was a very long and big introduction about all the topic. And the fact is that, as you know, when we want to implement something in the lab, we always have some noise. And in the same lattice you see, these superconducting qubits are subject to what's called the 1/f noise. So our purpose in our work was to study the dynamical noise to go toward an implementation. So let's go to the second part about noise. And I was mentioning the 1/f noise. Here you can see the spectrum. This is a so-called classical noise, a kind of classical noise. A classical noise is a noise in which our value is given by a set of classical states. So there is not like superposition or something like this, just a classical state of values, a set of values. And how can we describe the coupling of this classical noise to a quantum system? Well, we have an Hamiltonian that is function of this stochastic process that describes all the values of our noise. And the evolution is given by, well, now we have a density matrix, of course, because there is noise. And the evolution of our state is given by the average over all the possible histories, realizations of the stochastic noise. And we are averaging over this, and inside the average there is the single unitary evolution given by the single realization of this given noise. So here UDT is given by a certain Hamiltonian with that history of the noise, and then we take the average over all this. Well, in our work, we decided to start studying the simplest classical noise possible, that is the random telegraph noise. It is a noise that has only two values, plus or minus 1. And the value of the noise switches along time according to a certain switching rate, that is mu here. And the probability of switching n times in time t is a Poissonian. Essentially, we are switching, and the switching rate tells us whether the noise is slow, meaning a few switches along the time, or fast. So the value switches fastly during the evolution. We decided to use this noise because we implemented this noise model in our graph. Essentially, there is independent random telegraph noise on each link of our graph, and we are perturbing the hopping rate of each link. Essentially, in the case in which this is the noise strength, in the case in which we have dynamical percolation, this is the so-called regime, we are dynamically cutting and reputting the link in our lattice. It's something also done in classical network theory and so on. And then this Hamiltonian that is quite cumbersome is just the Laplacian matrix with a potential well with the open rates that are not all the same, but they are perturbed dynamically. Of course, the dynamics given by this Hamiltonian is very difficult to calculate, and above all, we have to take the average over all the possible histories, so it's very cumbersome to get the result. We did it writing a code in Julia. It is a new programming language. And we have written this code that is valid for any graph topology, any graph dimension, and generic noise model. So, and here you find the address. With this code, we can put noise in the classical dynamical noise in any continuous time quantum walk. We use it for studying a lot of things. For instance, continuous time quantum walk on the two-dimensional lattice, or then quantum spatial search, the probability of success, or also the quantum Markovianity, but in this talk, I will only talk about the probability of success. And okay, so to go back to the results, let's summarize a bit. We have our graph, generic topology. We want to find a certain target node here, and we apply noise to the graph, so independent random telegraph noise that can cut the links dynamically on each link of the graph here, all with the same switching rate and noise strength. And we have studied the results for some graph topologies. We start with the complete graph. We have defined two different scenarios for the switching rate, fast noise or slow noise. Well, what we see is that in the case of fast noise, we basically almost do not observe any effect of the noise. You see, this is the probability of measuring the target node as a function of time for different noise strength. And you see that even for dynamical percolation, they are all almost 100% of probability. For the slow noise, we see that it really damages our probability of success. For instance, for dynamical percolation, we are around 60%, so our algorithm can fail. And here you can see the maximum probability of success as a function of the switching rate. So we see that for slow noise, so we cut the links and they remain cut for the evolution, essentially, more or less. We have a damage probability, while quite surprisingly, if we cut the links, but we cut it very fastly, so we cut and then reboot, cut and then reboot. Oh. we don't have damage probability. We are almost 1. And to understand why this, here we can observe the evolution of the probability of being in each node of a complete graph. This is a complete graph, the nodes of a complete graph, with target node 5 for 3 different cases. And let's see the evolution during time. You see that in the fast noise case, we are almost following the noise less dynamic, while our slow noise gives a frozen dynamic. It doesn't manage to move from its position at a certain point. This is a very classical behavior of slow noise. For instance, in the same behavior, talking about quantum transport in nanoscale, fast noise gives the coherence that we don't observe here, but slow noise, and this is the point, gives localization, Anderson localization in a certain point. And we are observing something similar. Of course, it's not localization because we are starting spread all over the lattice, but the dynamics is frozen, like if it cannot move smooth. Okay, so what happens if we increase the dimension? Well, if we increase the dimension, we obtain better results. And this is intuitive, because if we increase the dimension, we are putting more nodes, so we are increasing the connectivity of the graph, the number of possible paths getting to our target node. So we are increasing the number of possible ways for the probability to get there. And if slow noise cuts one of these links, well, luckily, probably there will be another getting there. So we get better results. Let's move to another topology, the star graph with central node as target. Well, we see, again, the probability as a function of time, same effects. Fast noise, almost no damage. Slow noise jeopardizes the probability. Even more, the effects of noise are greater here. And it makes sense, because we have lower connectivity, only one link connecting each node to the target. So if slow noise happens to cut that link, then there is no way in which the probability remains stuck in that noise. We cannot reach our target. To better understand this, regarding the topology, we can observe again what happens when we increase the dimension. Here is the dimension of the maximal probability. In the case of slow noise, this time it doesn't change anything. And this makes sense, actually, because if we increase the dimension here, we are adding more nodes to our star graph, but we are not increasing the connectivity. The connectivity is always 1. There is always only one link. So we are not opening more waves, and this is why it doesn't change. So last graph dimension, and then we are free.
So in the case of fast node, instead it was, can you read also the graphic of the fast node? So
yeah, it's the same. If we increase the noise, this is the maximal probability. Here we are increasing as well, but as you see, it's something very tiny. So, the fact is that with fast noise, it doesn't make so much sense to speak about the connectivity because, we are reopening the ways. So, it's not so important. So, last topology is the star graph where the external node is a target. In this case, even fast noise damages a bit the probability, around 80% for percolation. Slow noise, well, the effects are tragic. We can almost say that our algorithm does not work anymore. Well, again, this is intuitive, because in this case, speaking about the graph topology, again, not only the connectivity is low, only 1, but also the degree of the target node is only 1. So if we happen that the slow noise cuts this link, well, our probability will never reach our poor target node, and so we fail. Again, we can think about it, if we increase the dimension, we see that in this case it's deleterious, increasing the dimension for slow noise. Why? Because if we add more nodes here, we are not increasing neither the connectivity nor the degree of the target node, because we have to add more nodes here to the central one. But we are increasing the number of possible wrong ways the probability can get starting from the central node that is the only connection with the target. So if something is going wrong, well, if we have more wrong ways, it will be even wronger. And so this was the last graph topology for our noise. And just to summarize all the results I have given in this talk. First of all, I have said, not proved, but you can find it in the paper, that the search on the star graph is optimal. I have also tried to convince you that this is really good, because our star graph can be a candidate for the implementation of our algorithm. Then talking about noise, we see that in general we can find this rule that fast noise usually does not jeopardize too much the success of the search, while slow noise is the true enemy in this case. And finally, quite a general result that we can find from our work is that topology matters. So every time we want to speak about noise in continuous time quantum walks, we always have to observe the topology of our graph to find whether it's robust or not against the noise. And in particular, we have to focus on the connectivity and on the degree of our target node. And here is the paper that we just put on the archive, where all these results are, and even something more. So, last part, just to conclude all this, some outlook. First of all, I will go now from October till December to work in Helsinki at Aalto University. And my purpose is to study 1/f noise, that is the noise I mentioned at the beginning that affects the superconducting qubits, so our candidates for the implementation of a quantum computer in general. And so I will try to study the effects of this noise and to plan the implementation, working with Sori Parauano, that has there at Aalto University a lab of superconducting qubits. So this is the first step. Another proposal, are there any further non-ideal experimental realization of our algorithm? This was something Roberta proposed us last spring in Turku. Yeah, you remember?
Yeah, I remember
Yeah.
the meeting.
Yes, but if we have a two-dimensional lattice, okay, we were considering only the first neighbor, but let's think to add an interaction between this node and this other node, that is also more physical if we want. Well, if you think about it, if we add all the interactions that will be obviously weaker if we are at distance, we are basically building a complete graph, no? Because each node is connected to each other, but it's a perturbed complete graph. There is noise on it, on the links. The open rates are weaker. So the question is, with this model, is it feasible to implement the algorithm on a model such as this? Speaking about the complete graph mapped on a two-dimensional lattice, do we have good results or not? And we have to investigate it. Then other possibilities is that we have the code now, so we can use it to study the noise for more problems. For instance, the quantum transport on complex quantum networks. This is something we can do right now. And finally, for a more theoretical approach, to study the quantum noise or the non-Markovian maps on our algorithm. Basically, we couple our system not to a classical but to a quantum environment, and we study what happens. And these are all things that we can do right now, and that are all quite interesting to discuss. Last thing, since maybe some of you already know, I will start my PhD here next January, and since this is a group of complex quantum networks, any suggestions that you can have for our work are all welcome. And thank you for the attention.
Thank you, Mark. Thanks for the very nice introduction. I believe there are other questions or comments. Maybe I can start here. One, you were showing a comparison between classical and quantum system, for instance, for the continuous time random walk, it was in Milano.
On the line, yes.
And what happened in the case you have studied, which would be the classical different there? Did you look at it?
Well, the fact is that there is not the same algorithm based on classical continuous time random walk in this sense. So we cannot describe such a comparison right now. I mean, what in the classical case, what we can do is getting our robot that is not quantum anymore, and just okay, this could be seen as a continuous time classical random, but at the end it's always like we are moving our robot in the graph, and the robot locally, this time only one node per time, it analyzes it till it finds the target node. So, I mean, classically, this is it, and it's not so different from looking in the phone directory till we find our number. So it's always something that it's of the order of n, and there is not such a true comparison with it.
I see a difference in the initial condition, right? Classically, you start with a walker in one spot, and then...
Yes, because there is no superposition.
In the quantum case is superposition.
Yeah.
Would that be equivalent to having n walkers starting from each of the nodes? Or not?
Well, n walkers
I mean, no,
in a quantum...
Any initial conditions? No. In the quantum case, let's imagine you start with a wave function which is localized in one node, and then you do your search. Then you do it again in another node. The average of results. That will not be equivalent to...
Well, it's a possibility. I mean, you can do it, and they already did it for the balanced trees, in which we have a sort of like the family tree, the same thing for a graph. They did the same, and they started in one node. The fact is that yes, I mean, a priori, I could not say now if we get exactly the same results, but I would say that there is a sort of mirroring of the two things, starting, I mean, just for experience, if you start from one node in this system to get to the target node, you can do it, and it can be clever. The fact is that at a certain moment, the evolution of this dynamics will be something like I start from the localized node, but it's not the target, obviously. My continuous time quantum walk spreads all over the node and reaches something that can look like a superposition, and then it gathers again in our target node. So I would say that the difference is not so much, but they actually did it, and it can be possible also for the experimental realization. It can be something we can study.
Just twice the time.
Yeah,
So you
I-
get any point, you spread, and then from the spread you go to the real target. So just twice what you get. But
Yeah.
it's not something for the end.
Yeah, exactly.
No, I think, I'm trying to make up a question, okay? I think the thing is you're not being fair in the comparison. Because in the classical case, you start from one place. But in the quantum case, you already start with a function which already has a component that you know yourself.
This-
One over n.
No, but I mean, it can be true, but the fact is that we can, from using quantum computation, we can build our state that is the superposition state. From the quantum computation paradigm, we can build it quite easily using the Adamart. I don't know if you know it. The Adamart gates. We can build quite easily the superposition. Easily means fast. So the fact is that it's true that maybe we have to consider, and they discuss it actually, to start in one node and then to get to the superposition and then run. Well, the fact is that we have to add a part, but this part is something like, for instance, as Roberto said, times 2, times 3, something like this for the time, but it's not of the order of n. It's not something that it's of the order of the number of nodes in the graph. So at the end, we always have a quantum order of square root of n, classical order of n. So the quantum speed up of quantum computation outperforming the classical one, we always have it.
Well, it's, I mean, there is a little more in there also. It's the same, this is that In the classical one, if you start, I mean, depends who the search. If they set one particle, in the quantum one, you can have spread the particle all over the place. In the classical one, you can have to one node at a time. So
Yeah, exactly.
wherever it goes, it will be more difficult. The thing is that it's different if you have many particles. In that case, in the classical one, you could also be spreading.
Yeah.
The different starting from a single point or starting from a spread circumstance. But I mean, in the case of quantum, you can do it with one. So
Yeah, exactly. This is quantum computation after all. Yeah, I mean, this is why quantum computation is good.
That's what we do with objective mechanism. We have particles that every time they reach a point, they multiply. You know, particles are always, there are also many particles in number.
no, because it's just in the classical one, all this formalism of the Planck and the probability and so on, usually it's thought for many particles. You have, you are in the limit of almost. And in those cases, the things can start to get closer to the quantum, but you need many for
This
doing
would be
the
interesting.
To put more particles in the classical.
The comparison classical and quantum give some advantage to the classical one.
Well, you
Trying to mimicking what you can do in the quantum case. Still, there is a difference because there you don't have coherences. But at least
Yeah.
you will be really comparing. Only
Yeah.
it will be just
in the quantum, you can also
assessing
put,
only the extra value.
you can also put more, but then you have to have in account this
Well,
symmetry.
to put more in the quantum case, I think it's a bit cumbersome because here the particles, the Walker, for instance, in superconducting qubits, is the excitation of our circuit, but can be in each one of the nodes, and we call this the Walker, the excitation, but it's not. I mean, it's a second quantization particle, let's say. So to add, I think, two excitation of our, I think it can become quite difficult to implement quite easily. But in the classical case, it can make sense. When I'm not an expert for the classical case, but if you study classical networks, it can be.
And the other question about the noise, because the thing that it was a little, let's say, but you are using the noise in the shooting, or I don't know how you call it, is that it's on and off for the links.
Yes.
I mean, I guess the noise was a little softer in the sense that they could not completely close the.
I don't know, but I studied this because when we see, this nu here is noise strength. For instance, this one, 0.2, is a very soft perturbation of the link. And here are the results. So as you can see, the noise strength, I mean, it changes the results, but not qualitatively.
Yeah.
So we always have the same things, but obviously if we put low noise, we have better results in general. So we studied it. I was mentioning the cutting of the links because it's, if we want like a more general, I mean the more interesting case in this case, because we are perturbing the links and not the energy of the nodes. So in this case, it's something very close related with the classical dynamical noise. And so
Well, I suppose that in microscopic implementation, it could be good actually with closing the link.
of course, of course, of course.
In a microscopic one, you have to understand that actually it's completely closed.
Yeah, it's true. And indeed, I consider this noise implementation more like not something like something for the comparison with the classical case, but when I will study this kind of noise, that is the true noise of superconducting qubits, we will put this noise, like because in the lab this happens, we will put this noise on the energies, not on the link. And then there is the possibility of adding noise on the link, but still. So you had a question?
I don't know. What if you had a classical random walk that is super diffusive?
I confess that I mean, I can understand the concept, but I have never studied super diffusive.
Because you showed that the quantum walk is super diffusive, but maybe that
Yes.
is also an unfair. Well,
No,
not, it's not unfair.
Well,
but,
yeah, exactly.
it's a quantum
I mean,
but,
it's quantum world that is unfair with respect to the
Well, they
classical.
have to compare with something that is also super diffusive.
Yeah, no, but in that case, the Laplacian, well, whatever it's the formalism in that case, because it could be more complicated, could be different, and then in the quantum translation, it would be inside also in the quantum Hamiltonian. So it would be also fast in quantum world.
I mean, yeah, I don't know.
The reason is fair, quantum is different. In that case, in this case, we will
I don't know how you build a super diffusive classical quantum random walk. How do you do it?
Well, I have like a level flag or something like that, but on
Okay.
my work that's more.
Yeah, more than one.
Okay, yeah. So in this case, I would say that it's the classical walk that is unfair with respect to the quantum. So
then you should do the same also in quantum one.
Yeah.
It's super. Okay, are there any other questions? Comments? If not, let's thank Marco again. We start the next talk in 2 minutes. Ok, siamo in quella è difettosa.
Then,
Esos son fotones, pero son plásticos. Habrá que mirarlo, sí. Pero sí, no sé si se pueden implementar. Sí.
tú los tienes también.
Los tenía y ya me deshice de un momento.
Es que había
Sí, da pena. No sé si se quieren mantener en el taller. Emilio, los pósteres estos guapos de la óptica Society of America pueden servir en algún momento porque son simplemente estéticamente guapos.
Se le haga una esquina de uno a quitarlos, que está dando.
Sí, pero si pueden a lo mejor limpiar
Sí, y que luego se sepa dónde está, porque se guarda yo.
Sí, hasta que dentro de 2 años alguien no te diga, mira qué guapo, tú puedes poner ahí. Sí.
Vale, bueno, les digo a Rubén, los meto al taller en los armarios del fondo, donde los armarios.
Lo que está roto,
problema es que hay
lo que está roto, tira.
Nunca se ve.
No hay un catálogo con la
colgarlos en
causa.
algún sitio, por ejemplo, en la sala de másteres y no me parece en la sala de despierto. Digo, porque si no, así sabemos dónde está. Y a veces se vuelca en un sitio.
Quello con più citazioni sarebbe un autoreciclatore armonici.
Con più?
Per mettere più citazioni nel sistema, anche senza avere problema di più di citazioni, perché avere più di uno naturalmente.
Bueno, por ahora lo guardo en mi
Sì, perché usando anche avendo più citazioni non singolo nome.
son 4. 4 son pequeñitos, un poco más y así de
Milano,
aquí cambia, igual, pero igual paso por lo del mar. Perché fuera en los armarios mismo,
e si riesce a lasciarle fuori tranquillamente. Sì, ok.
Se tu vuoi con un percorso perché no, praticamente.
Sì, certo, perché nel sistema ottico questo è più facile. Perché io ci in mente su questi presentati in qubits ho paura che questo dovrebbe essere un attimo complicato. Perché hanno già i problemi a controllare il numero di eccezione.
Non so quali sono, non so se sono di topologie sono di definizione.
Però non ho presente sistemi ottici, quindi vorrei fare così.
No, sono piccole di sono tutto il confronto quantistico classico ovviamente è sempre più